Section 11.2 introduces difference of means, and there's two different situations with difference of means. Either we have dependent samples or paired samples, or we have unpaired samples. A lot of times for paired samples, it will be pretty obvious. So like twin studies, you have one twin in one situation, another twin in a different situation, or the same person before and after. That will be a paired difference. And then unpaired, those two groups have no relation to each other. Often they're different sizes, but there's two different situations that we're going to look at. Mu d will stand for mu1 minus mu2, and it's just a symbol that's often used in the paired difference of means. Now this one here, this is the same as from the difference of proportions. So if it is all positive, then we can take mu2 to the other side, say mu1 is greater than mu2. If the whole confidence interval is negative, we can say mu1 is less than mu2. And then if it contains 0, both positive and negative numbers, if it contains 0, it's kind of the same way to say that, then you can't make a conclusion about the relative size. For the hypothesis test, it's pretty obvious because the alternate hypothesis is telling us the relative sizes. It has these as the alternate hypothesis. Now for the difference of means for paired samples, I just wrote here like the before and after situations, and twins, those are pretty common where there's a direct connection between those two groups. It uses the t-distribution, and the degrees of freedom in this situation is equal to 1 less than the number of pairs. Now here are the instructions for the hypothesis test, and note the number of pairs here. N is greater than 30, so N has a different meaning in this situation. This is still the number of pairs. This one here, it's less than the total population size, 5% of that total population size. So here's sometimes just to point out something that's done in the book very often. Mu sub d equal to 0 is the same as mu1 equal to mu2. They sometimes also do mu1 minus mu2 equals 0. You just have to take the mu2 to the other side, and it's the same exact thing. So if you ever do it by hand, here are the instructions. I don't want you to do it by hand. I want you to use the Excel files, and we're going to be using the hypothesis test Excel file. Yeah, here's the ones for the confidence interval. These are more for just reference. It might be a good idea just to print them out or to save the PDF somewhere, so you just have reference to these instructions just in case you ever have to take another statistics course, or reference out in the world. If you're ever needing to do a confidence interval, you'll have these instructions on how to do them. Download the Excel files as well. If you ever need them in the future, don't be afraid to send me an email. Okay, so let's do a couple examples. We're going to do one with data, and then we're going to do one where they give us the statistics. And this first one asks the question, do educational toys make a difference in the age at which a child learns to read? And to study this, researchers designed an experiment in which one group of preschool children spent 2 hours each day for 6 months in a room supplied with quote-unquote educational toys. A control group of children spent 2 hours a day for 6 months in a non-educational toy room. And it was anticipated that IQ differences, home environment might be uncontrollable factors, so identical twins were used in this experiment. and they give us the data. It's in weeks to read at a certain speed. And we can see most of the differences are negative. We don't have very much data at all. There's only 6 pairs. So not much data at all. But we can still do a hypothesis test, and it says do a statistical test with a level of significance of 0.05. So as always, our first step is to check the conditions. And for this one, does it say random sampling? It doesn't really say random sampling, but we can assume that they used random sampling. They probably did. If not, that would be a good thing to discuss with them. Okay, now the second one, it's not described as normal in the wording here, so we do have a bit of a problem here. So let's just write it's not described as normal. I would think it would be right skewed. And we only have 6 pairs. So this condition is not met. And that's a little bit of a problem. I'm going to highlight that in red so that I remember that we didn't meet that condition. We're going to proceed anyway. And 6 is smaller than 5% of all identical twins. Around that age. And we're good with that last one. We can assume that it's well, 6 is a super small sample size, so it should definitely be smaller than 5% of all identical twins. Now we're going to proceed anyway, so we'll write the null hypothesis, and I'm going to kind of strategically write this. I'll put mu, and this is the experimental group. This was the one with the educational toys. That's the first one. So I'm going to just subscript this with educational. And I'm going to say this is equal to the mean with non-educational. Okay, the alternate. And we have to double check. Doesn't really quite say the direction, but most of these are negative, and I would imagine that they want to show that it takes less time to start reading with the educational toys. So let's do a left tail test in this situation. The people who run the study were probably the people who made these quote-unquote educational toys, and this is what they would want to show. So this is probably okay for us to set it up this way. Okay, so now for this one, we want to use the hypothesis test. Excel file. And we want to use the paired difference of means sheet. And we have data, so we're going to use the right side. Okay, so, oops. So make this a little smaller. we're going to plug in the data. And that's pretty much all we're going to have to plug in. The level of significance, though, was 0.05. That's given in the problem. And then the tail direction is the only other thing that we would have to identify. And we're doing a left-tailed test in this situation. So I'm going to navigate to our hypothesis test one here. And go to the paired difference of means. So in here, and I have a lot of data here. So I'm going to clear that out. And I typed this already. So I'm just going to copy and paste these numbers in here. Notice one thing with this situation is that you don't want to type the differences. It actually calculates the differences. So just let it do that calculation for us. It'll do the subtraction. And I just want to double check these look right. Yeah, those look good. Other things for us to plug in, the 0.05. I have to type the word left in here, press enter. And we get a p-value from here. Oh, just going to copy this down. And I'll show you what I'm writing. Okay, so the p-value is 0.0228, so 2.28%, which is small. In this situation, we reject the null hypothesis. And when we reject the null hypothesis, we can make a conclusion about this one. So we could say there is significant evidence that the mean time for the educational toy room was smaller than the time for the non-educational toy room. Okay, now the next thing that we're going to do actually demonstrates a point that's super important. When we read this statement here, we think, oh, okay, significant evidence. But when we make a confidence interval, 95% confidence interval, we're going to see that this difference is not very big. And this is kind of a way that you can maybe manipulate the conclusion. So here, I'm just going to use the confidence interval Excel file and the same sheet. So use the paired difference of means. And then also the right side. So it looks nearly the same as the other one that we used, but we're going to see when we plug those in the only thing, okay, I just put this down to 0.95. Get our lower limit and our upper limit. So let's see what this is going to give us. And once we see this, we'll hopefully notice, oh wow, that's slightly misleading when you look at just the hypothesis test. So make sure you change down at the bottom paired difference of means. And it looks like I already have this one in here. Yeah, so I have the data in here, 0.95. And we're looking for this lower and the upper limit. So negative 4.6, let me just write this down, and negative 0.06629. Okay, now the units for this are in weeks. So this is weeks and weeks. If you wanted to see what this is in days, we multiply that by 7, since there's 7 days in a week. And it gives us 0.46. This would be in 464 days. This is less than half a day. So what this confidence interval is saying is that with 95% confidence, we can say that the educational toy room decreased the amount of time that it took to learn at that certain speed from less than half a day, but up to 4.6 weeks. Now, which one would be better for advertising? Well, this one, right? This one would be way better for advertising. We'd say, oh, educational toys can make your child read faster up to 4.5 weeks, or however they would want to advertise it. And very often that's what they'll do. They'll just report this one, and they'll, in the fine print at the bottom, or the thing that you're supposed to read that is way too long to read, they'll have this other information which really tells us that the difference isn't quite as large as it might have been like advertised. So you just have to be careful with that. Very often you'll see things done like this. So like this conclusion here seems significant, and then we actually look at the confidence interval, and they're both negative, but the smallest difference is pretty much negligible. Half a day, like, does that really make a big difference? Not really, I would say. Okay, so here's one last example, and this one has the statistics given to us, so it's a little bit different. It says a researcher is studying levels of serotonin in patients. The researcher randomly selects 50 participants and gathers data to get a baseline on their serotonin levels before given a new medication. The participants then take the medication for a few weeks, and the researcher then gathers data to get their new serotonin levels. The researcher subtracts the serotonin levels after from the serotonin levels before. Okay, so it's a positive difference, and then finds that the mean of the differences is 16 nanograms per milliliter, and a standard deviation, kind of weird notation, S subscripted with D, a standard deviation of 10 nanograms per milliliter. Now, looking at this is a huge standard deviation in relation to that difference. And so my initial thought would be that this is not going to show significant results. But let's go through it. So check the conditions. They did use random sampling. Oh, now the second one, our sample size is large, so n equals 50, which is greater than 30. That's good. And then the last one, this is just 50 is less than, the population isn't super clear, but it seems like it's really general, so just people. So we'll just say less than 5% of the population. I would assume just people who would take the medication. It's not super clear, but you could also just clarify with the researcher themselves. Okay, now our null hypothesis would be, I'm just going to write it this way, mu after equals mu before. Sometimes you would see it written another way, just mu d equals 0. And for this one, mu after is going to be greater than mu before. They're looking to increase the serotonin levels. Okay, this would be the same as mu d is greater than 0. So just a different way of writing that. Okay, now we're going to use the hypothesis test. Excel file. And we're using paired difference of means. And we're going to use the left side. Okay, now let's go there and see what we need. So over here, we need d bar. We need the standard deviation of the differences. We need the number of pairs n. Oh, and I'm looking at the wrong file. Good thing they're really similar. Okay, d bar, sd, n. Degrees of freedom are calculated, so that one we don't want to plug in. If it's white, don't change it. Level of significance didn't really tell us in the problem, I don't think, and then we need the tail. Okay, so going back here, identifying what they gave us, d bar is 16, SD is 10, N was 50 participants. It's before and after, that's what makes it a pairing. Level of significance, oh, it did tell us 5%, 0.05. And the tail we get from the alternate hypothesis, and this is a right tail. Okay, from this we're going to get our p-value, which I think will be pretty large, but let's see. 16, 10, 50. 0.05 is good, and right. Oh, actually, it is significant. Yeah. I guess because we're looking at the differences, and it is a big sample size, yeah. Huh, okay, so the p-value is just about 0, which would mean that we would reject the null hypothesis. Okay, so from this one, just right here, the p-value is definitely less than 0 is less than 5%. And so we reject the null hypothesis. Okay, now we can say there is significant evidence that the new medication increased the serotonin levels. Now, by how much is another question. I'm actually kind of curious, but let's look at it. So 16, these 3 go to here. Yeah, oh, okay, so yeah, because that difference is there, 13 to 18 nanometer, or whatever, or it is, nanograms per milliliter. Yeah, so I guess that might make a big difference. I'm not sure exactly how serotonin works. That seems like a small amount, but it does seem to increase it. So if that's a good thing, I guess our test has shown that it does its job.